Hi everybody, this is Ms. Rosita. We're looking at 4.4 today. These are going to be word problems. It's called modeling and optimization. So you're going to take what you've learned in the first 3 sections of the chapter about how to find mins and maxes, and you're just going to apply them to word problems. So as always, the word problems, the hardest part is, of course, trying to get the equations to start with, and then you know what to do. Take the derivative, find where it's 0 and doesn't exist, and so forth. So for starters, just some vocabulary. When you hear the word modeling, you always know it's talking about word problems. Optimization is just the process of trying to find the min or the max of something. And we learned in the first part of the chapter already the first derivative test or second derivative test to find the extreme values. Also, we have to, as we saw at the beginning of the chapter as well, you have to check endpoints. So don't forget that oftentimes with word problems, there's a domain that makes sense for the problem, and therefore you have endpoints. Or, of course, your places where the derivative is 0 or doesn't exist are places that extreme values could happen as well. So I put in here just kind of a 3-step thing to try to stick to as you're approaching these problems. First thing is, of course, you're always going to try to come up with the equation that models the situation. Okay, and this equation is going to be your primary equation, the one that you end up taking the derivative of. Sometimes there's a secondary equation as well. And that secondary equation, if there is one, it usually is just used simply to get rid of one of the variables in the primary equation that you're maximizing or taking the minimum of. The second step is finding your critical points as well as your endpoints, and you test them. You can use your first derivative test or your second derivative test, but you need to basically figure out which one is the min and the max. So min or max, usually it's one or the other that you're looking for in a word problem. And then the third thing is, of course, when you think you're done, go back and read the question one more time and make sure you're really done, that you've answered everything. And here at the bottom, I put in the little note. I highly suggest you draw a graph. So whatever the equation is in step 1, draw a picture of it so that you at least have a visual as to what to expect as the minimum or the maximum. Okay. Here's an example. This is a pretty traditional problem. We've got this area that we want to be fencing in. So it says we have 216 square meters of rectangular pea patch to be enclosed by a fence and divided into 2 equal parts by another fence parallel to one of the sides. So basically we have our picture. It says what dimensions for the outer rectangle will require the smallest total length. So if you're trying to fence this whole thing in, how can you arrange it so that you use the least fencing and keep your area 212 meters squared? And then also ask how much fencing is going to be used. Okay, so keep in mind the only real number they've given us is 216 for the area. So when I look at my perimeter, the total length of fencing, I have 3 x's and 2 y's that make up my length. So here, my first equation for the length that I'm trying to minimize is 3 x's and 2 y's. I also have the area equation that x times y is 216. So if we're trying to minimize the length equation, it's this one that I'm going to be taking the derivative of. Now before I take the derivative though, I have too many variables here. I have my length in terms of both x and y. So if I take this secondary equation, I can use it to substitute out one of the variables, x or y, so that I have my length in terms of just one variable. And that would be a lot easier to then go ahead and take the derivative of. Okay, so I chose to write my length in terms of x. Let me go back for a second. So x, if I write it in terms of x, that means y is 216 over x. So this y right here I'm going to replace with 216 over x. So here we are, 216 over x. I've cleaned it up a little bit, went ahead and took the derivative and set it equal to 0 and solved, and I got 12 and negative 12. And you also want to be thinking, is there anywhere that the derivative does not exist? Well, this x is actually in the denominator. Let's see over here. This x is actually in the denominator. So if x is 0, I'm dividing by 0, that would be undefined. So again, x being 0 is also to be considered, but of course x is the length of our fence, and of course we don't want that to be 0. So I don't think I have to worry about that too much. So I end up with my, when I set my derivative equal to 0, I end up getting 12 and negative 12. Again, x is a length, negative 12 doesn't make sense, so I stick with the positive 12. And if I go ahead and put it on a number line and check my signs on either side, I know if I'm to the left of 12, my slope is negative, and to the right of 12, my slope is positive. So you picture your curve going down and then at 12 it flattens out, and then after 12 it comes up. That must make 12 a minimum. If it goes down for negative and up for positive, right here at 12 in the middle must be a minimum. Okay, which is good. That's what we were asked for, to minimize the length of fencing. So if I know that x is 12, I go back, I figure out y is 18. Again, I just went to my xy equals 216 equation. And then it did ask me what the total length of fencing was, so if I have 12 and 18, I can plug those in and get 92 for my total length. All right, I hope that was okay. Let's see. The next idea is, instead of dealing with areas and so forth, we could be dealing with profit, revenue, cost kind of things. And I know you've seen this before, but I went ahead and put the slide in to remind us. So profit is always equal to the revenue minus the cost. So your revenue is how much money you're collecting, your cost is how much you had to pay for whatever it is that you're selling, and your profit is how much you're in the clear. So a few other things that we've seen in the past from Chapter 3, the average cost would be your cost equation divided by how many items you have. That would be your average cost per item. And then your marginal cost, marginal means how much it would cost to produce the next item. And this is the derivative. So if you're ever looking for the marginal cost, you take the derivative of cost and plug in the number they give you. So C prime of 200 would be how much it would cost to produce the 201st equation, or 201st item rather. Okay, and same thing holds if they talk about marginal revenue or marginal profit. It's just the derivative of the revenue equation or the derivative of the profit equation. And then in the blue box at the bottom, we have the maximum profit occurs when the marginal revenue equals the marginal cost. Well, that may be a little confusing when you think about it, but actually if you come back up here and you just think, oh, I'm trying to maximize the profit, I would take its derivative and set it to 0 and solve. So if I take its derivative, I'd get r prime minus c prime, set it equal to 0 and solve, you'd have r prime equals c prime. And that's exactly what this formula is. The minimum average cost, again, our average cost is c of x over x. We saw that right at the top here. C of x over x is average cost. And if I want to minimize that, I take its derivative and set it to 0 and solve. So whatever this fraction turns out to be, take its derivative and set it equal to 0 and solve, and what you'll get is the minimum average cost. Okay, so here's one to try. It says, suppose C of x is the cost of manufacturing x items. Find a production level that will minimize the average cost of making x items. Okay, well, we said just a second ago, average cost is your cost equation, C of x divided by how many items you're talking about, which is x. And if I go ahead and take a look at those things, my C of x equation is given, so I just write that out. X still on the bottom, and that has to equal C prime of x. So the derivative of this equation is what I've got over here. I then cleared the denominator by multiplying through by x, or actually no, I divided the top by x since all the terms have x in them. Anyway, and then I solved it on out, and I got 0 and 10. Now, I could use my first derivative test, put those on a little number line and see my signs, pluses and minuses. But I did that on the previous problem, so I thought this time I would go with the second derivative test. So I'm doubtful that x equals 0 is going to give me the minimum average cost of making 0 items. So I'm not really going to care about 0. But let's look at 10. If I plug 10 into my second derivative equation, well, let's see. Here's the first derivative right here. And so if I take the derivative of that, I would get a 4x to the first minus 20. Let's see. Oh, is that supposed to be 4 or 6? I wrote a 6 over there. Oh, I'm sorry. You know what? That's because I was looking at the simplified version. C prime of x is actually over here. So yes, the derivative of C prime. So derivative of this is 6x, and then derivative of this is 40, negative 40. So if I go ahead and plug my critical number 10 into the second derivative, it turns out a positive 20, and positive tells me that the graph is concave up there. So I know that if x is going to be an extreme value and it's concave up, it better be a minimum. Okay? That is what we were asked for, the average minimum cost. So now that I know that x is 10, I'd have to plug it back into the cost equation to get the actual cost of producing 10. Okay, so here's our practice problem. This one's straight from the book. I think it was number 12 or something like that. So feel free to give it a try, and then when you're all set, play, and I will show you the answers. Okay, so first off, they told me that the volume of this rectangular box is 1,125. And since it had a square base, the volume of the box is base times length times width times height, where length and width are the same. So x squared y. And I just got the y by itself. Now the cost equation is given to us. Now this cost equation, I wrote it in terms of x and y. That's how they gave it to us. But I have too many variables, so I decided to get rid of the y's, both y's here and here. So if I want the cost just in terms of x, I go back to the y equation. I figure how much y is, which is this right here, and I plug that in for both of the y's. Simplify it out, I get to here. This equation right here is going to be my cost equation for x number of items. So as I move on, I'm looking for when the derivative is 0. I need to take the derivative still. So taking the derivative of this equation, I get a 10x plus a negative 3375x to the minus 2. I set that equal to 0. I solve, and I see what I get. Let's see. Okay, so let's see. So I went ahead and simplified my c of x equation by plugging my y in for what the y's are in each of these. So here's my cost equation just in terms of x. And then I go ahead and take the derivative. I did it on the top here. Took the derivative and I simplified it by writing with a common denominator. So I would just have this numerator over x squared. I like to do that. I like to simplify my derivative before going into my little chart here. If I do that, then when it's a fraction, I have just the numerator equals 0 if I'm looking for when the derivative is 0. So I just have numerator equals 0. And then when I'm looking for when the derivative doesn't exist, it's the denominator that's 0. So in this case, x is 0. So I get when x is 15, the derivative is 0. And when x is 0, the derivative doesn't exist. So I go ahead and I look at that on my number line here. And here at 0, of course, x can't be any smaller than 0 because x is the length of the side. So I went ahead and started my number line at 0 and went off to the right. So if it's a negative between 0 and 15 and a positive after that, that makes it the function go down, flat, then up. So this 15 looks like a minimum. I did go ahead and draw just a quick sketch of it. It looks like it goes back up on either side. But as far as the minimum goes, it's right about in here. And that would be at 15, which looks somewhat reasonable on my graph. Okay. Now the endpoints, I already mentioned that it doesn't make sense for x to go negative. And then if, of course, your entire volume is put to one dimension, it would be 375. So assuming that our x is somewhere in between those numbers, we could go back and kind of see which ones are mins, maxes, and neithers. Well, we already identified this one as a min, and then these over here, they look like they would both be maximums, and whichever one is local or global, we would be able to tell from our picture, but actually the question was asking us for the minimum anyway, so not the maximum. So I don't really have to worry about endpoints. It's just the 15 that looks like it's going to be a minimum. Okay, and if I plug 15 in back for the x right here, 1,125 divided by 15 squared, I should get 5 for x. Excuse me, 5 for y. Okay. Thank you so much for watching. I think that is everything.